Today I'll talk about multi-GPU radiative transport in participating media with Kokkos. So I researched combustion. Combustion still powers about 80% of the world's energy. So on one side of the spectrum, combustion is really useful. We can use it to power our engines, such as gas turbines or piston engines. And in this aspect, we use combustion research to help us sort of maximize our combustor efficiency, to minimize pollutant emissions, to expand the system longevity. But then also there's the other side of the spectrum, so combustion can be quite harmful. And in this aspect, we're trying to mitigate the harmful effects of, for example, wildfires, or reduce the rates that they spread, or to try to optimize our suppression tactics or minimize their damage. So combustion simulations are really integral for all of these components, and if you do simulations of combustions, you can touch all sides of this spectrum. So I wanted to highlight two sides of the coin here. Essentially, this talk will be in two parts. I'll talk about forward modeling of radiation in combustion, as well as inverse modeling of radiation. And so basically the forward model here, the way I define it, is that we have some combustion solution where you have 3D varying composition and temperature from some CFD, computational fluid dynamics simulation. And in combustion in particular, you care a lot about what are the chemicals that exist in this field, what are the temperatures, as well as what are some kinds of rates of formation of these chemicals and heat formation. And so this is one side of the spectrum, and we try to bring it with the forward model to a radiation solution. And so this is more of a focus of this study today. And so with the radiation solution, which can be the incident heat flux to a wall, for example, the boundary of your combustor, or it could also alternatively be some kind of a measurement device where you have the radiation incident to an optical component like a sensor or a spectrometer. And here we define the inverse problem. What we're trying to do is trying to go back from this radiation solution back to those flame properties like temperature and composition and pollutant concentration and all of these components. And just also to highlight the math here, without getting too into detail. So some people are familiar with Beer's law if you did sort of a mechanical engineering heat transfer like background. This is just an equation that describes an exponential decay function, describing how the intensity of light will decay as it travels through some kind of a participating medium. And so if you shoot a laser through a large cloud, for example, the laser won't come out with the same intensity. It'll decay exponentially. It'll decay according to the attenuation of that cloud, but then also the distance that it travels through the cloud. And so those two components will combine. But that's only attenuation. In flames, we actually already have emission as well, and so it gets much more complicated. You have to account for not only the attenuation of that radiation, but also subsequent re-radiation or increases of intensity along that path length. And so all of a sudden, your problem becomes six-dimensional. You have solutions you're trying to solve in space in this 3D varying flame, but then you also have direction. For each point in space, you also have all points in direction. And then also you have a sixth dimension of wave number. And this describes sort of like your frequency of light that you're focusing on, because different frequencies will emit more or less depending on what's emitting. And so with it being a six-dimensional problem, it's very computationally expensive. And so that's where we sort of rely on accelerators to help improve this field of research. And so for the first part here, I'll talk about the forward model, and I'll highlight some work that actually has been done with a few other researchers at Oak Ridge, including Wenjin, Andre, and Damien, as well as my former advisor, Xinyu, at the University of Connecticut. So we use the Monte Carlo method. Essentially, we trace a bunch of random rays throughout the system. And this is great for high-dimensional problems, but it's relatively slow to converge with the number of samples that you have. And so the customary approach is essentially to emit rays at different points in this medium and trace these rays throughout the geometry. In this case, we're looking at a CFD mesh. So we have a bunch of sort of piecewise homogeneous representation of our scene, with each cell having its own components. And we trace this ray, and as this ray travels, it deposits energy into the cells that it travels through. And so this you can couple to some CFD simulation, and you'll have energy going into the cells, and the cells will be able to sort of have an accurate description of radiation. The problem is this is quite slow, and that's for two reasons. The first is that ray tracing is expensive. This is something that's been known for quite a while in, for example, the graphics processing community. With respect to simulations of fluids, this will be on the same order of runtime, especially if you have some kind of a chemistry component to it, where in your CFD simulation, you'll have some reacting flows, and resolving that chemistry is extremely expensive. The second is these types of models are extremely difficult to scale. So radiation is an all-to-all effect. So every point in your medium will emit radiation, but also every point will absorb. And so you have this physics which needs to be accounted for from all nodes to all other nodes in a domain-decomposed environment. And so it's very expensive to scale. And so I'd like to address both these problems. The first that we came up with was very simple. It's just to use a GPU. This is very well known for the graphics processing community, of course, but in this field, it wasn't very well known for specifically radiative transfer in combustion simulations. And so we use a variety of different techniques in Kokkos to help accelerate this. And these are listed here. Of course, the parallel 4 to conduct the ray tracing. And then, of course, we use a couple other parallel execution models to help accelerate. Because in particular, ray tracing is not only rays that are traveling in different directions and locations, but also each ray has its own wavelength. And so you can actually consolidate rays together and trace them in an ensemble. If they happen to be going in the same direction, just change their wavelength. And so the parallel execution gets much faster if you treat the problem this way. And I think throughout learning how to use Kokkos, I learned that these would be good options for how to do it, because it forced me to think about how to best optimize the code in reading through the documentation. I should also highlight, so we did couple this to a CFD solver, in particular OpenFOAM. OpenFOAM, if you're not familiar, is an open source CFD solver, allows you to simulate fluids, and it is also based in C++. And so the challenge here was how can we essentially grab all of the OpenFOAM data structures, pass them to a code based in Kokkos with an entirely different build system, with an entirely different structure. For example, we use Kokkos views, whereas in OpenFOAM, it'll be using all kinds of different things. And so a lot of that, I really had to dive in to the Kokkos internals and try to figure out the best way to translate this code. And one thing I managed to settle on is that unmanaged view is very useful, because OpenFOAM is based in CPU, and it'll have some representation of your domain based in its own data structures. But I could extract those pointers and essentially just pass them to an unmanaged view in Kokkos, and I was able to operate on them in Kokkos much more easily. Of course, there's a number of other parallel processes I used in Kokkos that were very helpful, including the random number generator. This is a Monte Carlo method, so that's used extensively. So the second problem was scalability. So how do you scale this up to multiple nodes in your HPC? And so to solve this, we used ArborX. So as I'm sure many are aware, ArborX is a bonding volume hierarchy based code. And so we took advantage of those capabilities, where we have a multi-node system where each node has its own cells inside of it. And so what we did was we realized we could formulate the radiation problem in a way that you can trace these rays asynchronously across the different nodes of your multi-node domain. And so what we did was we essentially initialized these rays at each point within their own node with a point and direction. And then we used ArborX to determine which other nodes that each ray will intersect. And using also ArborX, we're able to send out the rays to those nodes, trace them internally, and evaluate whatever the radiation solution is for them, and then send them back. And so that was a really great speed up that we got there. So it was a coupling of ArborX and Kokkos that really helped us solve both these problems for the forward model. And so I don't have too many results, but the ones that I do have are based on this simulation we have. So this is it's called a pool fire. It's a turbulent pool fire. It's a direct numerical simulation, so we have a very high resolution grid. And essentially, it's a sort of test configuration often used for understanding how fire works. So this would be like, for example, if you have some kind of an oil spill and it lights up. This would be an example of something like that. And so in simulating the radiation for this code, we were able to get drastic speedups over the existing approaches already embedded in OpenFOAM for the discrete ordnance method and P1, which are just different, essentially, radiation solvers, which are less accurate, in fact, than the Monte Carlo approach. The reason that they're preferred sometimes is because they're supposed to be computationally cheaper. But in fact, as you accelerate it with our Kokkos ArborX backend, we're able to make it even faster than the less accurate versions of the radiation solver. And so this is really great because Monte Carlo for radiation is actually the baseline people compare to. And now we're getting Monte Carlo to be even faster. So this sort of enables us to get the highest accuracy we can with radiation. And so now I'll talk about inverse modeling. And so this was a few years ago. This was work, the forward modeling was a few years ago. We completed that. And we decided that we wanted to focus instead on trying to go from the solution of radiation back to an understanding of what's happening in the combustion field. And the reason this is important is because when you do combustion research, it's really hard to probe the internals of your flame. If you're trying to measure NOx or if you're trying to measure CO2 emissions, you can't really just directly insert a probe because that will interfere with the flame itself and disturb the research that you're trying to do. And so optical measurements are really essential. And so we decided to look at the field of computer vision, which is working on a technique called differentiable rendering. And so this approach essentially is like tomography, but for basically any scene you would like. And so what they would do is they would take images of their scene, for example, this room, with RGB images, and given just those RGB images and the known positions of the cameras, they're able to reconstruct the whole scene. And then create new images from different locations and different perspectives. And so it's essentially just tomography, but using modern differentiable approaches. And here you're actually seeing an animation of how somebody used a hyperspectral camera to not only reconstruct the scene, but also to map out the materials in that scene to understand what the scene is made of. And so we decided to do the same. We did the same with our combustion simulation. And this is, again, based in Kokkos. I'll dive into the details there in a second. So our diagnostic, essentially, we have this flame on the left here, and this is just a simulation for now. And we have 4 cameras situated around that flame, and each camera is producing an image from its own perspective, a 2D image, a 2D array of pixels, where each pixel produces a spectrum in the infrared. And so given this data, given this ground truth measurement, we then construct an inference procedure, which is a nonlinear optimization process here, where we essentially parametrize our scene, namely how much CO2, how much NO, or what is the temperature at different locations. And using a differentiable model, we map those parameters to what our observation is in the measurement. And this is the same forward process that I just mentioned that we use to do that map. It's an ill-posed problem, meaning that there are multiple solutions for this 3D reconstruction that can reproduce those measurements in this case. And so we add a regularizer, which is this phi. Essentially, this phi just says not only reproduce the measurements, but also produce something that's physically realistic. And given those optimization procedure, we can then reconstruct the field, temperature and composition everywhere. And we tested, I won't go into details here, different ways to parametrize the scene with voxels, as you would with like a CFD simulation, and then also with a neural network, where you essentially just map the input location to some kind of temperature and composition and field value that you'd like. So the parameters here change, but it's all just a representation. And we essentially constructed this iteration procedure, and this relied on the forward model to map the ground truth to the measurement, or excuse me, the parameters to the measurement, and then we evaluated gradients. We had to code up custom adjoints for this in Kokkos, which was challenging and took time, but was accelerated, which is great. And given these gradients, essentially we can tell the parameters how they need to adjust slightly to better reproduce the measurements. And we iterate, and within this nonlinear optimization procedure, we're able to get a reconstruction of the flame. And so it worked really well. So here's just a visual. I think I'm running out of time here. But this is a reconstruction as a function of the iteration of how the flame actually gets reconstructed, and it does a really great job. And this is the different representations. I won't go into detail here, but essentially we're able to reconstruct it in all kinds of ways, voxel grids or neural networks, and it does a really great job. And so I think I'll wrap up here, and I'll be glad to take any questions, but that's a summary. We essentially went through forward and inverse modeling of radiative transfer. I really glossed over a lot of details here, but if you have any questions, I'd be happy to take them.
So what's the condition number? How bad is it actually conditioned? I mean, he needs the mic.
I know we only have one.
Yeah, so it's a very, very ill-conditioned problem. I can't tell you the exact number, I don't know it, but I can tell you actually it's almost certainly just ill-posed. Because, yeah, I mean, because we don't have the whole spectrum, in fact. And the species we're trying to gain sometimes emit outside the range of the spectrum we have access to, meaning we have no information on it. So it's ill-posed, yeah.
Okay, in that case, like, how much do you trust independent of how to do it on the HPC computer?
That's a great question. So depends on what you're looking at. Temperature, you can get an understanding of what the range will be. And I have a pretty good trust of what the range will be. I don't think I'll trust specifically in this location it'll be this value. You can look at the structure. I think I have a pretty good trust in the structure of the reconstruction of the flame. But again, at a specific point, I don't think I know exactly what it is. And so for combustion researchers, that's sort of good enough, I think.
I have a question about your build system. Since you're coupling Kokkos and OpenFOAM, ArborX, and probably with PyTorch, how does your build system look like?
So that's a good question. I had to write a lot of my own build system. I just wrote a big bash file essentially that goes through and compiles OpenFOAM, the solver, and then couples it to Kokkos and essentially calls CMake and does all the steps. And then the PyTorch part, I had to use like PyBind. And so I essentially had the initial part with the compilation with OpenFOAM and Kokkos, and then I wrapped that to a PyTorch layer. So it really is just kind of all one big bash layer hack. Okay.
One more question while we're switching speakers.
Oh, sorry. Yeah, go ahead.
Oh yeah, so I was kind of curious about how, like, because you're in the first part you were coupling the just OpenFOAM simulations with the Monte Carlo method. How does the density on each rank look like? Like, do you have some MPI ranks that just have essentially no fire or no combustion things going, and you're still like tracing into those? How does like the load balancing look like, I guess?
Yeah, so currently we don't do any load balancing. Essentially, we decompose the way OpenFOAM wants to, and we trace the rays in that way. There could be fire where there's no need to trace rays in that region. So right now, I think that's something we need to look at. Is there a better way to load balance? People have come up with ways, but we haven't actually implemented any yet.
Yeah, thank you.
Yeah, thank you.
Thank you.